All right, let's give it a minute or two. Hi, everybody.
Hi.
We'll start at 801, 802. What would you like to do?
Yeah, I think it's live. Hey, we have 28
Okay.
people watching already.
Okay, cool. All right, let's do this. Hi, everyone, and thank you for joining us today. And before we get started, I want to let you know that this webinar is going to be recorded and we're going to make it available later on our YouTube channel. My name is David Muriel, and I'd like to introduce our experts, Sabrina Aquino, Jenny Suchodolskaya, and Atita Aurora. And today's demo is focused on the storage and retrieval of multivectors. As you may know, Qdrant is one of the few vector databases that supports multivectors. However, this process can be complex and computationally demanding. So our goal today is to explore how to optimize this. We're going to be talking about ColPali, which is a powerful visual language model that's capable of generating multivector embeddings for images, text, and PDF files. And the thing is, these ColPali embeddings, they can be very resource intensive. So we're going to demonstrate how to compress them using quantization and in some other ways as well. Specifically, today Sabrina will comment on how quantization works with ColPali embeddings whether this method actually truly improves performance. After that, Jenny will try out a pooling method to reduce the number of vectors involved in search calculations. And finally, Atita is going to show us a practical business use case where an enterprise might actually leverage or build a RAG solution with visually rich documents and use ColPali for embeddings and search. So overall, I think this is a very significant webinar today because many of our users have vast troves of data they've gathered over the years, some scanned files, PDF files, or documents in other image formats. So if they can find a cost-effective solution and an efficient way to convert this data into vectors, they can unlock the full potential for organizational chatbots, agents, and much more. So before I stop talking, I just want to let you know that the notebook for this webinar is going to be posted in the chat very shortly. So you're going to see and be able to follow along with all the code. And as we start talking, we also recommend that you create a Qdrant Cloud account and get your free cluster, no credit card required, because you're going to need the API keys sooner or later. So we're going to drop the links in the chat for you to access. That's it for me. Please go ahead, guys.
Thank you so much, David, for the introduction. And I'm super happy to be sharing the stage here with two amazing engineers, Jenny and Itita. And we're also, like they've said it all. Like, we're going to be covering a very interesting topic in retrieval today, which is ColPali. And then we're going to further talk about how you can optimize it and how can you apply it in your own data using quantization, RAG, and so on. So super excited. Thank you everybody for joining. Hello, Connor. Hello, Pavan. I see you there. Theory. So this is the agenda for the presentation. And here we start by explaining why is ColPali outperforming some of the existing standard methods out there for text extraction and processing documents. What are some of the challenges faced today by libraries when they're trying to parse PDFs? And also, we're going to explain the way ColPali works, which is by applying contextualized late interaction into vision language models. If you don't know what none of that means, don't worry, we're going to be covering all of that. And also showing some actual benchmarks of how good is ColPali really, how good ColPali works, using the Vidori benchmark created by the creators of ColPali. We're also going to be showing two hands-on demos. The first one by Jenny, where she uses ColPali as a reranker. And the great part here is that we are managed to get the retrieval speed of ColPali faster 13 times, which is amazing. And the second one is going to be presented by Atita, where we use ColPali and RAG applications. Finally, we're going to be having a Q&A, so if you have any questions, please drop them in the chat, and we're going to be answering them afterwards. Okay, so let's get started by talking a little bit about like the standard PDF retrieval methods. And that's what most people are doing today to be able to extract data from PDF. And here's the breakdown of each step, and it starts with parsing techniques like OCR and layout detection. And these two parts extract the structure and the content of the PDF. Then we use like chunking methods, like we use chunking, semantic chunking or traditional chunking to split the text into smaller sections for a text embedding model, and also captioning to describe the visual parts of our documents. Then these text embedding models are converting these into vectors that we can use to a vector database. Basically, for the online phase, we split the query into tokens and also like do some similarity metric around it to retrieve the most similar vectors. And the thing here is really the big problem here is in this first part of the retrieval, where lots of mistakes can be made. So let's talk a little bit about like what can go wrong when processing those PDFs. And it's basically, we can see here that traditional text extraction methods really work well when you have easily searchable PDFs. In this example here, we're using the State of Data in AI document by Databricks, one page of it, and it's a basically searchable PDF, meaning I can copy paste it easily. I can see here that in the text extracted, the first part, which I can easily search, is basically extracted kind of correctly. But when we go to more complex layouts, like this table right below, we can see like the numbers don't match the exact information that they are associated with, meaning that this data would be unretrievable if we wanted to embed it or basically put it in our vector database. We also have like this type of use case where we have like scan pages, right? This is very common, old archives and so on. OCR methods are very hardly capable to extract the data of these pages in a way that's really readable. It gets lots of information gets lost. Honestly, hardly anything is usable, and lots of errors are made when you use this type of scan page with traditional methods. There are many libraries which can help you to do this, but there's a lot of fine tuning that you need to do, and some better, some worse, but some of them, like most of them, don't get good results, as we're going to see ColPali having. And okay, so as I mentioned before, VLMs are a very important part of ColPali. And it's one of the reasons why it's able to get information from visually rich documents. So here's a little breakdown of how VLMs work. And the first step of a VLM is like processing images and text as inputs. Those images are flattened and mapped into an embedding space via linear projection. The text inputs are tokenized and transformed into embeddings, so both of them have the respective encoders, both the images and the text. We also have a projection layer right in the middle that's going to align both of these embeddings into a shared embedding space. And then we use a language model to transform the output that's going to be a text. So again, we have images and text as input and text as output. Now let's see how VLMs are being used in the ColPali architecture. Okay, so ColPali uses VLMs to handle visually complex documents without requiring any OCR. So the architecture of ColPali actually is very simple. Overall, it's very simple. The first step is to split the documents into smaller pieces, which we call patches, and these patches are processed by the vision encoder of our VLM. Then basically, the extracted visual embeddings are going to be passed through a projection layer, like we talked about, projected into a higher dimensional space and incorporating all the spatial information. We're going to be seeing this more in depth in the next slide, but then those those embeddings are aligned with the text embeddings, like we saw before, and then we use a late interaction mechanism similar to CoBERT to generate multivector representations for both the document patches and the queries. Let's take a deeper look into how all of that work in more detail. So here we have an example of a page being divided into a grid. ColPali divides the pages into a 32 per 32 grid, and this results into 1024 patches. This basically means that we have 1024 multivectors per page. This is just a concept image, it's not an actual 32 per 32 grid, but basically this is a lot of multivectors per page. Then still on the offline phase, we have the processing of our document patches until the final embedding is ready to be stored. So each image patch is processed by the visual encoder, basically to extract the visual features of that patch. And then we have a linear projection layer, which is the very important part, which is basically preserving the spatial layout of the patches within the documents. This part is very important because it allows the model to understand the relative position of the patches between each other. So it's very important later on for us to be able to have contextualized embeddings. And then those contextualized embeddings are fed into a large language model for semantic understanding and projected into the projection layer, having our final 128 dimensional patch embedding. And then we just repeat that for all 1024 patches per page. The next online phase of ColPali, we're processing the query. Basically, we're able to find the most relevant documents to the query after this processing. And the first step is to tokenize the query to generate the embeddings using an LLM for each one of those tokens, and use the same projection layer as before to align with the patch embeddings in the same space. So here we're working with multivectors for both the query and the patches. So we're going to see how we're going to be able to retrieve the most similar patches to our query vector. And that's exactly how the late interaction mechanism of ColPali is coming to place together. Basically, it computes the patch level similarity scores during query evaluation. This makes sure we have a very precise ranking when comparing the query with our documents. To compute the similarity scores, we use something called maxim, which is basically what's happening in the right side of this equation. The relevant scores indicates how closely a patch matches the query based on the computed similarity. And for each query token, we compute the similarity for all document patches. We're going to see how this works better in this next image, where we can see the entire retrieval flow. So during the offline phase, which is shown like here in the right side below, the patch embeddings are computed and stored as multivectors, and they retain all the contextual information. And the query tokens as well, they're processed and compared each other with document patches using dot products. So basically, Maxim selects the highest dot products for each query token, and these maximum scores are summed up to compute the relevance score. And the relevance score will tell us just how relevant the query, the page is to our query. And this actually allows ColPali to get a very highly accurate response to retrieve documents, because it's going to be able to retrieve the maximum similarities across all of our tokens. And here we can see like how good is it really? Like if we actually do the benchmarks, how good does it perform? So the creators of ColPali faced this problem early on, which is there was no easy way to benchmark vision models against each other for document retrieval. They created this benchmark called VDORE, where they tested ColPali against a number of other methods with many PDF files. And the first part we can see here, they compared it against unstructured IO, which is a very well-known library. I think everybody knows it for parsing documents. So at first they used BM25, and they also used BGEM3 as the first one, keyword-based searches, and the other one is a great model for dense vector representations. And they did the same thing here below using OCR and captioning along with the text extraction. They also compared it with other vision models alone, like GinaClip. But what we find here is that ColPali, which is basically vision language models plus late interaction, like we showed, outperformed actually by a large margin all of the other methods that we currently have in terms of accuracy. And you can find these results in the actual official ColPali paper into how they perform these comparisons and how it works. But yeah, ColPali is really good, but it's also very computationally heavy. So if you're working with just 2,000 documents, which is not a lot, you're going to be working actually with 2 million multivectors, which is a lot. So it's time to get into action, knows how to actually work with this large scale. And I'll hand it over to Jenny with the demo on ColPali as a reranker.
Thank you. Okay, let's then exchange the sharing screens. And let's begin. Okay, so the first thing is actually, I want to know if everybody tried to use ColPali in something like production, more than on 1,000 points or something. If so, please text in the chat, because in our Discord community, I saw from time to time people writing like, how? Okay, so today we're going to explain you how. So at some point we noticed what is actually a big pain of everything, to use ColPali in an actual vector database on an actual amount of data, not 1,000 points for experimenting or demoing, but when it actually comes to some solution, say it's a visual RAG, Atita is going to show you something later. You're not going to do a RAG on 1,000 documents, you're scaling more and more. And then you come to the realization that ColPali provides you more than 1,000 embeddings for a one page. That is so much. And why it's so much? Okay, our vector database is strong, and other vector database is strong too. Of course, there are like optimized algorithms, HNSW indexing algorithms, so we can literally accommodate billions of vectors. But still, think of it. When we do search on, when we are building vector index, for example, HNSW1, we compare a point to point to check their similarity. Then think, one point is 1,000 vectors. Then when you compare it to another point of 1,000 vectors, I mean these patches here on the screen, I stole a slide from Sabrina, I am that smart. So when you compare this 1,000 to 1,000, that's already a lot. Then throw in dimensions of ColPali, throw in at least 20,000 pages, which is what? A book. And then you have 2.56 trillions of comparisons if you just compare them between each other. That is so much. So we thought, okay, people will start building stuff, and they will start building it on Qdrant. They will start thinking that the problem is Qdrant. But actually, the problem is the amount of multivectors in ColPali. So how can we optimize it? So firstly, of course, we researched what is out there. And for example, Vespa provides a lot of nice solutions to that, like binary quantization, Hamming distance, and some parallelization. I left the link. By the way, this demo is open sourced and now in repo. It's going to be in the chat. So if you just want to play with it around, please feel free. Write me on the GitHub. I am super happy to any collaboration. So, okay, there are some solutions out there, but they all work around optimizing vectors, like maybe with quantization, with reducing their precision from float 32-bit ones, or maybe using some parallelization techniques. And there is a very simple idea that when you reduce the amount of these patches, basically when it's not 1,000, but say 100, your speed, your computational resources, they drop quadratically. Because as you see, we basically use 2 times for each point the amount of vectors. We compare 1,000 to 1,000. Imagine how easier it is to compare 100 to 100 than 1,000 to 1,000. Okay, then we thought, how can we actually reduce this amount? And of course, everything great is done before us. We just need to use it somehow. So we thought, okay, let's try pooling. What is pooling? I think machine learning engineers plus minus know it, and also a lot of IT guys, but I will remind you in general. Imagine we have this picture with these patches. What if instead of throwing away some patches, because each patch of this image is actually important, it can contain the information that we're trying to retrieve. What if instead of throwing it away, we'll just compress them together, somehow sum them or take a maximum or do some operation? We thought, okay, we can try that. And we saw that nobody tested that before. But if we just do it, we just use some popular type of pooling, max pooling or min pooling, we might actually lose a lot of quality of retrieval. Like why ColPali is so good. It's so good because it actually is astonishing in retrieving PDFs. What's the point to, again, make it faster, but butcher the quality? Then you can just use OCR. So we thought, okay, we can just pull them. That would be too simple, and use them as a retriever. What if we pull them, we save them, so we get much less vectors, we do a first stage retrieval with them, and then we re-rank with original ColPali vectors, so 1024 or something like that. How it will work? Will it work with min pooling? Will it work with max pooling? Let's test on actually big amount of data. So we did it, and spoiler, it worked out well. So think about this setup. Our decision was to test two types of pooling, max and min pooling, and we decided to pool it by rows. So basically, we have here 32 rows and 32 columns. So imagine instead of 1024 patches, we, through the pooling by rows, get only 32 vectors. How much less it is than 1000? It's like a lot. So imagine how much faster it is. So we were like, okay, let's just pool by rows and let's just test it on some very big data set. So here I'm coming to a more practical part. Now we have all the theory behind us. So I'm using here a Qdrant cluster. As David said in the beginning, you can also use a free tier one. And I'm using here this version of ColPali. This is the configuration you can see later of my cluster. It's not a free tier one, but it was used for experimentation. So it's not a recommendation for production. For that, reach out separately in Discord community. We're always answering. So here I configure a collection for my experimentation. It's a very specific configuration. I decided to put all vectors in RAM because we wanted to test the speed of retrieval with ColPali, original vectors, and our approach without any cache on disk situation. But of course, when you do it in practice, it's a little bit different. Of course, I left all of these notes in the notebook. And then we decided to select some dataset for experiments. But since we couldn't find anything out there in the open source, which would work perfectly for retrieval with PDF datasets, unique PDF pages, and queries related to them, retrieval queries, we basically combined one. So it's Vidore, I don't know. Sabrina need to help me out here. I'm just saying Vidore benchmark, the one that was mentioned before. It's a UFO dataset for which of all of our DevRel team need to say thank you to this amazing author, Daniel, because he literally provided us with the materials for the next year. His data set is amazing. I also left a link on the page where he explains how to generate it. And I used doc-VQA dataset. It's not specifically for retrieval, but for en masse, it worked well. Okay, so here, of course, it's trivial to upload data and to process data. But since we never lose the opportunity to teach how to use Qdrant, here I left basically the code of how to embed and upload in batches. As you can see in batches to Qdrant, the vectors created, the initial vectors of ColPali, and the max and min pooled one. There is one little note, which is funny but important to know, that each time we're speaking about theory, we're saying that there are 1024 vectors per PDF page. So if you look here, it's 32 by 32. But actually, it's 1030. And it's interesting why. If we check what the tokenizer of ColPali returns, we can actually notice that at the very end, they prepend the prefix, basically saying that you need to describe the image. So this 6 additional vectors, you need to know that it's exactly to this specific tokens and the textual postfix. So we decided we're not going to delete it. So we're just going to pull 1024 vectors together and then just keep the special tokens. So as a result, we basically had, instead of 1,030 length-long ColPali vectors, we had a 38 length-long ColPali vectors, 32 pooled, plus 6 specific tokens. And here is the function of upload. It's pretty, I hope it's pretty well explained in the notebook, but if you will have any questions, please reach out. And we got our collection. Let me actually show you it a little bit in UI. So here's our cluster, here's our demo, and here you can see when it will load that it has basically PDF pages here, amount of them. Then it has like the page link, it has the query associated with it, and we have 3 vectors. The initial one, 1030, mean pooled one, and mass pooled one. Okay, so we uploaded everything. We have everything successfully set up for the experiment. And now it comes the most interesting part, to see if our initial retrieval with pooled vectors and then rescoring with ColPali gonna work as good as the initial retrieval with original ColPali. So this is the second notebook. They're all in the repo. And here we have the basic setup in the beginning. We can skip it. And let's talk a little bit about the setup of the experiment. So how we can measure speed and quality fairly. So nobody can say that, I don't know, it just looks good, but it's not good. Let's select 1,000 queries. So let's test quality and speed on average. And for each query, let's retrieve top 20 PDF pages returned by Qdrant and ColPali Maxim metrics. Okay, so firstly, we thought nice idea would be just to sample 1,000 queries from our dataset. Here I'm just casually showing you that you can randomly subsample 1,000 points from Qdrant. Everything is, by the way, in the repo if you want to see like the random samples or something else. But you can see that these questions, for example, this one, they are not so good when it comes to retrieval, because this question, what is the date mentioned in the given page, can literally be answered by every second PDF out there. So we needed a specific retrieval data set. And honestly, thank you to Daniel, literally saved us. UFO dataset has perfect queries which define the retrieval task and on which we could actually test everything. What do I mean by defining the retrieval task? Check it out. This question actually probably can be answered only 1 or 2 PDF pages in the collection, the specific ones. So we have like a relevant query. So we subsampled 1,000 queries from the UFO part of our dataset, and then we began our experiments. The only one thing that I want to show you before we are going to look at the meat of this talk, basically, it's how ColPali also processes queries. It's pretty interesting. It also creates multivectors for queries, but at the very end, it adds a lot of path tokens. And I just thought, what about if we just cut them away? So one little TP trick at the end, which we are going to use later, is also cutting these path tokens away. How exactly, it's going to be explained in this notebook. Okay, so there is a code to embed the queries with ColPali. Here we embed everything, and now we're coming to the experiment. So
Jenny,
we need, yes.
Sorry, before you move on, we have 2 questions that I think are very relevant to this part here specifically. So I'm just going to quickly ask, which is, what is the retriever user here? And then how big are the resulting HNSW indexes?
Can you repeat the first question?
Yeah, the first question is, what is the retriever user here? Used here, yeah.
ColPali.
Yes, we're using ColPali. And how big are the resulting HNSW indexes?
I didn't create HNSW index to original ColPali at all, because this size is going to be incredibly large. And it's literally the point of this webinar to show that it's insufficient to create it. And for the HNSW indexes for the pooled embeddings, I can separately measure and report after the webinar. You can come to me in GitHub or somewhere, and I'll be happy to report how big they are. Yeah, to explain about the retriever, I'm actually coming to this part. So it's basically multivector retrieval here. We're using ColPali as embedding model. We're storing vectors created by ColPali in the database, and they are compared between each other. And this is the similarity search happening out there. And we are trying to basically show how to do it effectively when we use pooled vectors. So 38 vectors created from the original ColPali vectors as an initial retrieval, and the original ColPali as a reranker. So it's actually ColPali as a retriever and ColPali as a reranker, but the ColPali as a retrieval is the one that we optimized with mean pooling and max pooling. Okay, so let's come now to the setup of the experiment. So we needed a ground truth situation, something that we are going to compare to, something that is going to show that, like, what is our basically standard. And here we want to prove that our method works as good as original ColPali, but just faster, much, much faster, actually 13 times faster. So the ground truth is to search with the original ColPali with 1030 vectors per point. And here we're using exact search, no HNSW, because we didn't want to accommodate for any additional amortization, mistakes, and like index, how to even formulate it. Like, we wanted to be as precise as it could be. So we run it. This is our ground truth. This is how it's supposed to be. And you can see that it actually works 30 seconds per one iteration. I'm doing here batch search. So you can, again, use the information how to do batch search in Qdrant. And per batch of 8 points, we're spending 30 seconds. That is a lot. I mean, of course, it's also a network problem because I'm using Colab and I'm using cluster. And if we did it locally, it would be much faster, but it's still a lot. Nobody is going to use it in an actual application. So now we truly see that we need to do some optimization. And here we're setting up our optimization technique where we are checking what if we initially retrieve 200 points. So we're selecting an oversampling scale factor of 10. What if we retrieve initial points with pooled vectors of ColPali, so with these 38 vectors we created, and then rescore them and select top 20 out of them with the original 1000 ColPali vectors? If we use this method, is it going to be as good as retrieving with original ColPali, 1000 vectors, no index? Of course, here we're using index for retrieval. HNSW is built for the pooled vectors. So we can see that there is a function doing that. And now we need to check if max or min pool is actually going to work as a first stage retriever. And we see that the pace, where it was 30 seconds before, dropped to 2.5 seconds. It's 13 times faster. So imagine what is 13 times faster. We can see that relatively it's a magnitude, and it's an order of magnitude. But of course, I mean, it was expected. We are now searching with only 38 vectors instead of 1000. I told it, it's quadratical. We're going to improve the speed. But is the quality as good as it would be if we would just use original ColPali on everything? Okay, so how can we measure the quality? For that, we're using ranks library. My colleague Casper recommends it a lot, so maybe you heard it already. And we are using, there is like some supplementary functions that you can check out what I'm doing to apply this ranks library. But basically, we're choosing 2 evaluation metrics. I am speaking on this big breathing, time to breathe out and continue. So we have this evaluation metrics, 2 of them, and I selected in DCG at 20. We have top 20 query, top 20 documents retrieved for every query, and recall 20. So basically, if both of them are close to 1, that means that whatever our 13 times faster approach retrieves, it's basically the same as original ColPali model would retrieve. So ColPali model retrieves top 20 documents of these numbers, and basically our approach retrieves kind of the same ones. Then both of these metrics will be very high, close to 1. So we decided to use them and to check, and you actually can see if we are using the mean pooling as a prefetcher in Qdrant, the quality is very, very good. And you can understand that 20 queries, it's a lot. 20 documents, I'm sorry, 1,000 queries, 20 documents. It's a lot. So basically out of 20 documents retrieved, on the very top, maybe top 18 of them are the same as would original ColPali retrieve. So basically, if we replace original ColPali with our method, we're not going to lose anything in retrieval quality, but we're going to speed it up by 13 times. Then we experimented a little bit more. We decided, okay, let's cut out this path token from queries. Let's maybe try binary quantization on the prefetch. It turned out to be a little bit faster. You can check it out. And it turned out to be a little bit worse in quality. So it's always use case specific what is more important for you, quality or speed in this trade-off. In conclusion, we tested and we understood that basically the fastest method to make ColPali workable in real-life scenarios is to use its pooled version as the first stage retriever and use original ColPali as a reranker. It's much faster than any other methods because it actually improves the speed basically quadratically, in the sense that we removing the amount of multivectors, we are basically changing the situation in the quadratic manner. So we're encouraging you to test any other approaches, and we're going to do, of course, it ourselves. So, for example, check column pooling, check more types of rescoring, half precision vectors, combining binary quantization and oversampling, and any other ones. But for now, this is the solution to go. And how you can actually practically use it. So where do you need this? Where do you need when you actually know how to work with ColPali efficiently? Now Atita will show, because she will show an actual application of visual RAG on top of optimized ColPali.
Absolutely. Thank you so much, Jenny. And just before going to Atita, there's a question people are really interested in knowing about more. So let me just share here on the screen, which is by Ion Popa. How does ColPali address challenges like context preservation and semantic understanding when retrieving documents from multimodal data sets?
I'm sorry, how can we retrieve? What does mean here by multimodal? Like we're working with PDFs, right? So it's one modality, image modality. I haven't seen ColPali working with anything but images. So what do you mean exactly by multimodal? I mean,
yeah, maybe you can talk more about that. And one of the things ColPali uses for being able to, do things like context preservation is the late interaction. So the contextualized late interaction, it is able to understand the patches along with the spatial elements surrounding it. So it understands the context within the patch, how much it is relevant to the token in the query, and also where it is located within the document. Are the things surrounding that patch also relevant to the query? And in that way, is able to put it all together using a vision encoder. And after the projection layer is able to actually retain all of that semantic understanding of each patch related to each query token. That would be my kind of short answer to it. Maybe Atita, if you want to add anything to it.
I think Yeah, I think you touched on something really important. I would just add maybe a little bit to it that one of the key things that we need to understand is that it is basically considering everything as an image. I mean, that's one of the ways it kind of keeps everything together. I think I saw a really good maybe a use case that was presented at the conference that I am right now. So hello from Lithuania. I'm in Vilnius and I'm attending one of the other conferences, and thanks for this opportunity that I get to talk to you guys as well today. So the use case that they presented here, not with ColPali though, but I think totally a valid use case, is that they basically, screenshotted the images from a video, and they used another model to kind of generate the description of that image from that video. And I think they used a combination of a vision LM along with the other text aspects in combination to kind of generate the context and the semantic understanding in the videos, if video was one of the key things that this question was targeted for. But rest of the other things, I think it's more of like getting rid of the context of chunking, basically. So you don't really have to kind of chunk in a way as you would the text data. So everything is processed as a snapshot or kind of image. So that's one of the things that I would like to add to your answer. Otherwise, I think you were going the right direction altogether.
Amazing. And
Okay,
please go
so
ahead and into the demo.
yeah,
Should we
sure.
answer
I was actually
beforehand, or are we switching to the questions at the very end? How do you think?
Yeah, we're going to the questions at the end, so please just drop them in chat, but we're gonna just answer after the second demo.
Okay, then thank you very much. And Atita, you go on with a practical example, and I can try to start answering in the chat, for example.
That's wonderful. Aren't you amazing, Jenny? And amazing description. And Sabrina, thank you as well. I think you guys have set the stage so amazing that I don't really need any slides, but I'm still going to be kind of, just giving a visual aspect to the problem that I'm dealing with. So as a solution architect, obviously, when I'm working with the clients, there are some things that are kind of like really tricky. Like some of the clients have very visually rich PDFs where they want to process like the text as well as like the images part of it as well. So this is just kind of like an example of the PDF or the images in PDF, which is heavily structured. And if you would have tried like other techniques with it, I would be showing that in a minute as well. Something that I just built for kind of, preparing like the context that where am I coming from. When I tried this with the traditional methods with OCR, I think you would all who would have tried this already would know that we completely lose the structure. And I think this is something where the problem comes in, because the RAG that you're trying to build or the question answering system that you're trying to build completely loses the context of each of these, fields, how they're related to each other, and how to construct the answer, which is as contextual and grounded to the text which is provided. One of the other things that would be maybe if you go to the next slide, is something that we would struggle with, is that when you have to deal with infographics, for example, or you have to deal with the charts, and I'm trying to ask the question, and the question is actually contained in this pie chart. So this is currently is the limitation that I had been hunting. So I'm not really going to kind of talk about all the techniques that I worked with, and all the kind of failures. Maybe that I can say for another talk, maybe that the techniques that I tried and did not really work out. I would just show you something which is something as an engineer, you would try. So you would try to kind of, go ahead, maybe pip install some PyMu PDF. There's a new version as well with the PyMu PDF for LLMs as well. And even if you try that, I think I'll probably take on the screen, Sabrina, and I'll just go ahead. Maybe.
Yes, please.
Yeah, I will take that, and hopefully I am sharing the right screen. I hope. Yes, I am. Okay. So as I said, I had the screens open on my machine as well, but then, so this is what usually one would try. You would try multiple kind of, OCR tools or, something to read the PDF. And for the context, I have this data set as private because from the client, I mean, obviously we're not allowed to make it public, but I would be making something public for sure for you to play around with. So this is like one of the examples of the pages that we were dealing with. As you can see, this is very data heavy, plus a lot of, structured text that's been applied, which makes it really hard for us to work with like existing techniques. So what I tried was like, I tried to process it through like PyMu PDF for LLMs as well. And I was able to generate really good meta text around the pages, but not really like the structured text as I would expect it to be. So even if I tried it with the markdown, I mean, I would just lose all the structure. So I think this is where most of our customers, struggled with when they try to leverage these kind of, PDFs for building a RAG. And I think these PDFs are like really huge in size as well. So it was really hard that you would process so much of text, and in the end, you would come across like the blob of text, which is not really usable the way you would want. So I'd go through this example, and I am saying sorry that I'm not going to make this example public, but the other one public as well. So this is the context that I started working with. So as you can see, that this is a private data set that I have. But then to give an example, I mean, I have shown some of the PDF pages that I was working with, and this is client data. So just to kind of show, these are, again, very structured tabular data. And I think you've seen in Jenny's example and also in Sabrina's presentation, how this is going to be processed. Like you declare the model and then processor. Obviously, you would create a quadrant collection, no brainer. I think so. I think Jenny gave amazing presentation there. And we're going to be uploading everything, like all the pages. So the pages are basically, the PDF pages are converted into, as you can see, JPEGs. This is a very nice, I think, if someone can post from the Daniel's maybe blog post as well. Otherwise, a simple utility that can generate PDF pages as an image from the big PDF files. So then you upload everything onto Qudrant. Again, this has already been covered, and you would find that also in Jenny's example. And then we look at the example collection properties. So yes, I used binary quantization as well. I tried with scalar as well. I think it was slightly a bit better with the binary, while my other example that I would be open sourcing in a bit, that I have sticked on with the scalar quantization because I was losing a lot of quality on this part. So this is just to ensure, because my data set is about 8 PDFs, as if I would probably show you from maybe in the beginning somewhere. Yeah, I have 8 images or 8 PDF pages, so to say. And what we're trying to do here is that we're just ensuring that everything is indexed. As you can see, 8 PDF pages are already indexed. So we had questions, for example, like what is the max temperature of the fabricated section of P355? Honestly, P355 is more like a model. It sounds like maybe machinery, and that's what it is actually. The other question, which is again very kind of very centered towards an exact or a specific number, what is the minimum power factor of HV motor at full load, or the additional restrictions applied to ferritic materials, and anything that is mentioned here as question, and I'm taking it as part of the requirements that were given to me. You would see that how restricted they are and how specific answers would have been expected out of this. So we convert our queries into multivector as well, because we will want to search them through the multivector way. So as you can see, for the first question, which was talking about the max temperature for P355, I hope I say it correctly, is it's somewhere on this page. At least we see that it's able to pull out the page correctly. So as of now, I'm sticking to limit 1 because my data set is very small. So I see that it's able to pull pretty much the right page because it's P355. If you want, I can make it slightly bigger just to kind of show the aspect of like the page that I've pulled. And as you can see, I think the answer probably would be the max temperature is 410. That's what I'm hoping is the answer that the system was probably looking for. So the next thing that I'm going to be doing is I have been able to retrieve my relevant images from the multivector store, Qudrant store. And now I need to give this resultant image that I've retrieved to my vision language model so that it can process and read through the images and then generate an answer for me. So that's exactly what I'm going to be doing. I have split this into two methods, because this is more of the experimental part, and which is why I wrap them into a method that I can reuse later. So search images by text. So this method basically does pretty much the search query and gets me the search result, which is the image ID or the document ID that I later on kind of iterate through my data set and pull out the exact image that matches the search query. So that's what I do. I process that through. So search by text and return images. I just did it one more time just to ensure that everything is working fine. And this is like for my second query, which is about the minimum power of the motor. I think I see something like HV motor, minimum power, hopefully. So what I tried to do next was I tried to club everything in a very traditional how you would combine like retrieval with the generation part. So you would basically stuff your context with the appropriate retrieved documents, and then you would pass it on to your generative model. That's what I tried to do. So I tried to use the Llama model, and sadly, because I'm in EU, it was kind of not allowed, but I leave it there. I mean, maybe could be useful to someone who's not in EU. So I go with my favorite OpenAI model, and this is where I'm basically encoding the image and then processing the images for the query response. So this is where I call my method, search by text and return images that we've seen earlier. So I pass this on to my LLM as part of the just a normal context that this is what you want to, this is what I expect you to answer. So I go through the first question, what was the maximum temperature? So I pretty much got the right answer. Then was the minimum power question. If you want, we can go back to the question as well, but it was like something to do with minimum power of the HV motor, I guess, minimum power factor of the HV motor, and the something to do with quadratic material. Let's go back once again and revisit the questions. So second time I did the HV motor minimum power, and seems like, and this is something that really impressed me, because it says that the document you provided, so the image that it actually retrieved, it is not specific, because it seems like it's mentioned on 9.2. Apparently that was mentioned on the page, that this is on 9.2, and the page that we probably picked up was 9.1 maybe. And it said like it's hard for me to refer, and which is why you have to go back to table 9.2, because I'm wondering, I'm retrieving only the first document. I increased my top K, and this is the time when I actually got my answer as I expected. So as you can imagine, like it would be very hard for me to go through like, where's my answer on this entire PDF? This just made it easy. And all of them are kind of clobbered in this really heavily structured, like tabular format with images. And I don't know if you already noticed that the table also had the images of the part that I've spoken about. Another one was the quadratic material, and I think you can see the additional restriction part that's already been taken care of. And I think that's also like a really big page, and it kind of summarizes that the nominal temperature should be this, and the short-term fluctuation should be this. One of the other things that I had on my slide earlier was, and I think Sabrina also had that on her slides, is somehow making sense of these pie charts or infographics, so to say. And that's something that I am going to be open sourcing, and I'm going to be dropping this link soon. So this is obviously something that we've already done, and the data set for that as well is open sourced. If you look at this one, that's already there, hopefully. Yes. So this is where, this is a 212-page report. So imagine if you're interested in something really specific about state of AI report, you would have to really scroll through, find it. So what I did was I just converted it into data set. So as I said before, like you could just go ahead and convert them into images, store them in a data set, going back to my example. So yeah, this is where I'm indexing everything. And then I start asking all of these questions. So just to confirm that I'm able to see, like this is the data set that I've indexed, and I create like a collection called ColPali State of AI on Qdrant. And yeah, pretty much the same way that we went with the other example. And this time I actually sticked with the scalar quantization as a set because I wanted to make sure. This is also very text heavy PDF, by the way. And quickly would like to show you some of the things. So it's like, what is the process of shrinking the memory requirement of LLM by reducing the precision of their parameter called. And I just wanted to see if it's able to basically pull out the right page. And it was able to pull out the right page. So this was like the first stage retriever through ColPali or the multivector supported by Quadrant. And then we went on and obviously created the similar search image by text and search by text and return images so that we can provide the images to our vision LM and it can prepare the answer for us. So I tried it once again just to be extra sure that I'm able to retrieve all the right context. So what is the state of RAG evaluation from the given report? It was able to pull out 2 appropriate pages. And then comes the point where I'm looking for example, like what are the root causes of interruption during Llama 3, 4 or 5 billion pre-training? As you can see, the answer was basically contained in this. I can go back to maybe the presentation just to show you. It is basically talking about like faulty GPU being one of the major factors, then the software bugs. And I'm assuming that it should be able to summarize, and that's exactly what it did. It was basically able to summarize everything that the hardware failures was the biggest cause. So it's basically summarizing the infographic for me: cluster inequalities, continuous monitoring needs, misconfiguration, arrival of components, and power supply issues. So it was basically able to summarize all the factors that actually influenced. And I love it that I don't have to, really get into the infographic and prepare all these kind of, statistics by myself. So definitely blew my mind moment with ColPali. I think that's all I have from my side. I would give back the control to you, Sabrina and Jenny.
Thanks so much, Atita. Patrick has said, Sabrina, Jenny, Atita, you rule. And I think you also, Patrick, had a question, which is, this is awesome and very promising. Do you have an intuition where the smaller embeddings would not deliver the same results? I think this is related to the Jenny's demo.
Yeah, it's actually a very good question. Thank you. I think it might not work if in every bit and piece of PDF you have, like in every smallest part of PDF, you have the important information. Maybe if it would be 2 specific numbers in a very detailed tables, then it might not work that great because you would need a specific little part of the image, not noise, not mixed with everything else. But in general, I think it's safe to use it.
Yeah, I think also related to your demo, it says this is exciting, but also very surprising given the loss of information. Do you think there was a big loss of information doing the pooling?
I mean, it's definitely happening because we compressed 32 patches, 32 vectors in one. That's why there was another question about, can we just pool all 1024 patches vectors into one? And here I would say, I don't think anything is going to work good with this setup because that is too big of loss of information. Here we're losing it by 32 factors, then it's going to be by 1000. So I don't think it's even going to be a good experiment.
Awesome. We also have another question by Ian. He says, does the retrieval pipeline involve a multi-stage process from coarse-grained to fine-grained retrieval? And how does the cross-attention mechanism analyze the selected candidates?
So the first question answer is yes. It's exactly what's happening. So it's basically, firstly, it's more coarse-grained, it's pooled vectors, they are more rude approximation of the page, and then we do a fine-grained reranking retrieval with the original ColPali vectors. And the cross-attention mechanism, I think here it's as it is happening in original ColPali, we are not using anything additional related to attention mechanism, we just do a simple pooling. So we basically aggregate the information, which all was taken into account while the cross-attention mechanisms in ColPali worked.
Great. Atita, would you like to add anything? Not really. Any more
No, I
questions? Yeah? Any more questions, please? Everyone, feel free to drop them in the chat. Atita, were you saying something?
No, I was just saying that I think that summarizes, and I think that that's pretty well explained.
Amazing. There's no more questions. We actually hit the 1 hour mark. So thank you everybody for joining. This recording will be available on YouTube afterwards. We're also going to be making those slides available as well with the links to the demos that we showed here. So everybody can take a look afterwards. So thank you.
Perfect. Thank you.
Thank you very much, guys. That was awesome.